In Unit 6, we will be dealing with spatial analysis. First, I'll discuss some introductory concepts in spatial analysis, then operational data models, then geometric and related operations. Spatial analysis in many ways represents the heart of GIS. It is how we understand our world, by mapping where things are, how they relate, and what it all means. What actions to take then can be decided based in part on this spatial analysis. So there are these questions of why, and then where. Understanding where is about putting the world in context. Information, understanding distribution, area, perimeter, and other factors that help define feature placement. Relations, what role relationships such as proximity, coincidence, overlap, visibility, and other factors play in location and occurrence. Detection, understanding and quantifying patterns of type and frequency over time. So these are a few of the uses and needs for spatial analysis, and we'll see some examples as we go through the unit. First of all, operational data models are an important part of spatial analysis. Basic spatial operators are important in spatial relationships and relations methods. So the point is to look at issues of equality, disjoint, which would mean where something is not connected, intersects, where something connects, touches, where two objects or features touch, cross, such as two lines crossing, defining within, so something is within something else, something contains something else, or there's an overlap, and then a relationship spatially relates, tested by checking for intersections between the interior boundary and exterior of two components. And in the Chapter 6 tutorials, you'll be working on some basic techniques of putting these different spatial relation methods to use. Then spatial analysis itself. These are some of the basic spatial analytical methods that you'll use in Unit 6 and beyond that in your use in GIS overall. So, distance, the shortest distance between any 2 points in the two geometries as calculated in the spatial reference system of this geometry. Buffer, all points whose distance from this geometry is less than or equal to a specified distance value, such as putting a buffer around a point. A convex hole is of this geometry. It gets into zones and boundary memberships. Intersection is the point set of intersection of current geometry with another selected geometry. Union is the point set union of the current geometry with another selected geometry. Difference is the point set difference of the current geometry with another selected geometry. Symmetric distance is the point symmetric difference of the current geometry with another selected geometry. Logical XOR statement. Geometric and related operations. So one of the important things to keep in mind is that there are many ways to geometrically modify data within GIS. And this is very useful because the type of data that you have and the output that you want to generate need to match. In other words, you need to make decisions based on how you'll be using the data that you have at hand. Polylines and polygons may have a large number of segments, and this may be considered overly complex or poor representations of the original features. It may be unsuitable for display and printing at map scales. So for example, you could start out with point weeding, so removing some of the unneeded points that are just basically providing redundant information. Simple smoothing techniques, which allow you to eliminate sharp angles that might be a distraction. And spline smoothing uses an algorithm in order to effectively generate a path that is representative from a statistical point of view of the original data while smoothing and simplifying the line. Some combination operations include intersection, where the result includes all those polygon parts that occur both in A and B. Union, where the result includes all those polygon parts that occur in either A or B, so it is the sum of all the parts of both A and B. Not, where the result includes only those polygon parts that occur in A but not in B. sometimes described as a difference operation, and exclusive, which includes polygons that occur in A or B, but not in both, so is the same as A union B minus A intersection B. Classification is another aspect of spatial analysis that's very important in terms of being able to produce especially thematic choropleth maps, and also to classify data and understand then ways to represent it. So some different classification schemes include unique values, where each value is treated separately, for example mapped as a distinct color. Manual classification, where the analyst specifies the boundaries between classes, required as a list, or specifies a lower bound and interval or lower and upper bound plus number of intervals required. Equal interval or slice. The attribute values are divided into a number of classes, with each interval having the same width and range of those number of classes. For raster maps, this operation is often called slice. Defined interval is a variant of manual and equal interval in which the user defines each of the intervals required. Exponential interval is where an interval is selected so that the number of observations in each successive interval increases exponentially. Equal count or quantile intervals are selected so that the number of observations in each interval is the same. If each interval contains 25% of the observations, the result is known as a quantile classification. Ideally, this procedure should indicate the exact numbers assigned to each class, since they will rarely be exactly equal. Percentile plots are a variant of equal count or quantile plots. In the standard version, equal percentages are included in each class. Natural breaks, or jinx, is widely used within GIS packages. These are forms of variance minimization classifications. Breaks are typically uneven and are selected to separate values where large changes in value occur. They may be significantly affected by the number of classes selected, and they tend to have unusual class boundaries. Typically, the method applied is due to jinx, as described in Jinx and Caspel, in turn follows Fisher. See Figure 422 in the textbook for more details. You'll see that natural breaks and jinx is often used in choropleth mapping, and you'll be comparing different methods of mapping the same data to show the great variations in results that you get. Finally, there's standard deviation. The mean and standard deviation of the attribute values are calculated, and values classified according to their deviation from the mean. The transform values are then mapped, usually at intervals of 1 or 1/2 of standard deviations. Note that this often results in no central class, only classes either side of the mean, and the number of classes is then even. Okay, that concludes the discussion of the introductory lecture for spatial analysis, and we will then turn to some more details in the next lecture file set.